The part of the galaxy around us is an area of the universe explored sufficiently well by now. However, it's a really tiny portion of the entire cosmos. Nobody can say with confidence what space objects may lurk in its depths several million light-years from the Earth, and most of them are likely to remain undiscovered for quite a long while. But just imagine that several radio signals sent at regular intervals from an unknown source in space are simultaneously detected on our planet. Many people would believe them to be emitted by something developed by an exceptionally advanced civilization. This was the conclusion arrived at by scientists who encountered the phenomenon of pulsars for the first time. July 1967. A series of pulses was detected with the help of a radio telescope at Cambridge University by a postgraduate Jocelyn Bell. They emanated from a pulsar as yet unknown at the time, and the results of the observations were kept secret for several months. The object was initially designated LGM-1, which stood for Little Green Men. The name was given following the assumption that these perfectly regular pulses were not a natural phenomenon, but signals of artificial origin, supposedly transmitted by an alien civilization. Besides, the team of scientists under Jocelyn Bell discovered 3 other sources of similar signals. The phenomenon took 7 years to investigate, and the thesis advisor of Jocelyn Bell's team was later awarded the Nobel Prize for studying this celestial body, which was subsequently dubbed PSR B1919+21. This pulsar was the first registered phenomenon of its kind. Its source was to be discovered several years later in the constellation Vulpecula, or Little Fox, 2,283 light-years from the Earth. Information about PSR B1919+21 was made public in February 1968, and by 1969 the number of detected pulses of this kind reached 27, and the term pulsar was coined as the official name for these objects. The first discovered source of this signal was the object dubbed PO943. It was spotted by Soviet astronomers in the Leo constellation. One of the most widespread assumptions at the time regarding this discovery was that all pulsars were in fact ultra-powerful radio beacons of extraterrestrial civilizations, and the pulsating signals remind one of a lighthouse twinkling in the night. However, it wasn't long before astronomers agreed that the regular signals were most likely emanated by neutron stars. Today, it is posited that these impulses originate as a result of a neutron star's spinning, and are in fact thin beams of radio waves. They are detected by the observer at precise regular intervals, which accounts for the pulsed appearance of this emission. Approximately 1,790 pulsars had been discovered by 2008. All of them were powerful sources of impulse radio emissions in space. As for the pulsars closest to us, they are located several dozen light-years away from the Sun. After pulsars were first detected, other pulsating sources of similar nature were registered by astronomers. They were described as powerful flares of regular intermittent X-ray emissions. Thus they got their name, X-ray pulsars. X-ray pulsars are also highly magnetized neutron stars, but unlike radio pulsars, which use their own rotational energy, X-ray pulsars are powered by accretion disks. An accretion disk is formed from material captured from the companion star, with the latter eventually becoming a white dwarf with all of its resources depleted. Thus, the mass and spin rate of X-ray pulsars gradually build up during the course of their revolution. As for radio pulsars, they on the contrary slow down as time goes by. For example, the average radio pulsar completes one rotation within the period from several seconds to several tenths of a second, with X-ray pulsars completing hundreds of rotations within the same time period. One of celestial bodies of this kind was discovered quite recently, and it is located rather close to our system. The object was dubbed J1023+0038, and its source caught astronomers' eye as recently as at the beginning of the 21st century. However, its pulses reached the Earth only in 2017. This was the first ever millisecond optical pulsar to be discovered. In essence, such celestial bodies are neutron stars as well. With a rotation period ranging from 1 to 10 milliseconds, the spin rate of these pulsars is several times that of regular pulsars. They form part of binary systems, and their spin rate increases to incredible speeds as the direct result of the pulsar pulling material from the gaseous disk produced by its companion star of a smaller mass. It should be noted that when a neutron star is in its active accretion phase, we see it as a source of X-rays. When the rate at which it pulls the material drops, bright pulsed radiation can be seen in the radio and gamma spectra. To date, a few more pulsars of this transitional kind are known to science, which fluctuate between the X-ray and radio spectra in a similar manner. However, it was the first ever transitional optical pulsar with a spin rate of this intensity discovered by scientists. The rotation period of J1023 plus 0038 is 1.69 milliseconds, which is 0.00169 of a second. The object itself is 4,500 light-years away from us. The mass of its companion star is 0.2 that of the Sun. It takes the pulsar 4.45 hours to orbit its companion star once. To date, the properties of J1023 plus 0038 have not been investigated in detail, although it is likely to be a not very massive neutron star. Although the object was initially considered to be a radio pulsar, in 2013 scientists noticed that its impulses regularly subsided and it was known to flare up in the X-ray spectrum. According to scientists, this phenomenon may be accounted for by the fact that the pulsar was at the moment in between the phases, which looks like the following. Radio emissions occur when material from the companion star is pulled to the pulsar, but star wind does not allow material to form an accretion disk. That is why the gas cannot heat up much and looks brighter in the radio spectrum. In the second phase, the stream of material from the companion of J1023 plus 0038 gets stronger and forms an accretion disk around the pulsar. The disk is in fact the source of observable X-ray emissions. It wasn't long before millisecond pulsating was detected in the optical band of J1023 plus 0038. As testified by earlier observations carried out with the help of the Swift X-ray telescope, the neutron star was surrounded by an accretion disk at the time. According to those in charge of the studies, the pulsar may have started to flare up in the optical band due to electrons in its magnetosphere when these electrons' speed was close to the speed of light. In the future, astrophysicists plan to conduct additional observations to study processes taking place within this binary system. And now to the object of the kind located furthest away from us that is known to science. It is NGC 5907X1, a celestial body which is also the brightest of all pulsars discovered by now. Spotted in 2017, this pulsar is an ultra-bright X-ray source. Shockingly, it releases as much energy in one rotation period as the Sun produces in 3.5 years. Earlier, astrophysicists believed these ultra-bright X-ray sources to be black holes. However, after the discovery of NGC 5907X1, it became known that they may turn out to be pulsars too. The object is located approximately 50 million light-years away from our Sun. As for its spin rate, it is variable. For example, in 2003, the rotation period of the pulsar was 1.43 seconds, whereas in 2014 it dropped to 1.13 seconds. Just to compare, if our Earth were to be able to change its rotation speed in the same manner, a day on our planet would last just 19 hours. Modern astrophysical models cannot account for the intense luminosity of NGC 5907X1, although scientists believe it to have something to do with a powerful multipolar magnetic field that may be concealed within the pulsar. It will take even more complex studies to find out the reason for the emission of such staggering amounts of energy. Just a few decades ago, the phenomenon of a pulsar was beyond any explanation. And today, science is able to differentiate between this phenomenon and any other in space. Our civilization strides forward, which leads us to believe that even this century may reveal a number of other phenomena unheard of in the past. The universe is like a giant canvas with quite a few blank areas. As our knowledge about space builds up, the pattern on the canvas gets altered too. With regularly applied changes, it may soon turn into a fully fledged map of our enormous universe explored by man.